All right, welcome back to part 2 of the series where we're making a static executable game on Linux to run just using the Linux kernel, using x86, 64, assembly, and C. And if you remember in part 1, we created this start symbol, which was would just pass to C the information that was provided to us by the kernel on the stack at program execution. And we also created this assembly syscall symbol that would translate a C function call into a system call to the Linux kernel. And then we use those to implement the write and exit system calls. And then we implemented a little Sterling function helper so that we could write a hello world program that would say hello from the program name, which is the first program argument, right? So we just wrote the hello from. We wrote the program name, which is argv bracket 0, and we used Sterling to get the length of that null terminated string. Then we wrote a new line. Okay, and if we run it, I believe already built from last time, but dump cycle hello from /dump cycle. Okay, so now it's time to talk about a little bit about what I mean by a static executable game that runs just using the Linux kernel. So usually when you would make a game to actually distribute to people on Linux, you would want it to interact with their window manager, their Wayland compositor, their X server, whatever display environment they're using. And for example, if I open a terminal here right next to my web browser, the web browser is given a window by what it thinks is an X server, I believe. Qt browser is using X. But my Wayland compositor is pretending to be an X server for it. And then this terminal is also drawing somewhere where the X server, the Wayland compositor, provided it. And then the Wayland compositor is what's actually putting all that stuff together on the screen and providing the pixel buffers to what gets sent out to this monitor that I'm seeing. What we're going to do is something a little bit more low level, is we're going to write a game that's going to draw directly to a screen using the Direct Rendering Manager subsystem on Linux. So all we're going to need to have available is a Linux kernel that has the drivers installed to provide the Direct Rendering Manager and the evdev subsystem. The evdev subsystem is what we're going to be able to use to get keyboard input to have input to our game. And it's not going to be able to run on a system that's already running a Wayland server or an X server. It's going to expect to be able to take over the screen and draw to it. Because of that, I've decided to make this video just about how to get up and running a emulated Linux environment where we can test our game once we get to the point of actually drawing pixels to the screen. So the first thing we're going to need to do is download the Linux source code. And kernel.org, the Linux kernel archives, is one easy location for this to grab this. And I'm just going to take the latest long-term release, which is this 6.12 tarball, copy link address. And then in our home directory, we can wget this. It's a fairly big file, though, and I don't want to wait to download it. So I am just going to copy it out of a little prep directory I've created. OK. And we can extract that. While it's extracting, there are more dependencies you're going to need to be able to build the Linux kernel. There's a full list here. You're not going to need all of them, so you can kind of install what you have on your system and try building the Linux kernel with the configuration we'll set up later, and then install things as you need it. On Void Linux, what I ended up needing is if we do xbps query tech-m, if you can see there's more here than what was installed in the last video. I needed to install the BC basic calculator. I needed Bison and Flex, which are the parser generator and lexer generator. I needed elfutils devel, which is elfutils plus the devel means we get the shared libraries and such associated with it. And similarly, I needed OpenSSL devel, rsync, and xzip. And there's a few other tools here. Towards the end of the video, I'm going to show how to make a bootable USB drive to actually boot our kernel, our Linux system that we create on a real computer. So I installed GRUB and mtools and XORISO for that. But for now, we're going to look at building the Linux kernel. So let's clear here. OK, so we have our Linux source code. There's two ways you can build the Linux kernel within the source, which puts the object files and other build artifacts inside the source directory, or you can create a separate directory. I kind of prefer keeping those things separate, so I'm going to make a directory build Linux, and that's the directory we're going to use to build our kernel in. Now, if we go into the Linux kernel, the way you configure the Linux kernel is with a series of make commands. So the most basic command you can run is make defconfig. And because we're going to use a separate directory for our target build, we're going to provide this a variable O, which is going to be a path to our build's target, which is going to be my user and then that build Linux directory we created before. And then I'm going to do defconfig, which is the default configuration for the current system, current architecture. Ooh. Oh, config. And it's going to take a second, but this is setting up the default configuration for x86-64. And we're going to need to run one more command, which is I want to run this in a virtual machine, right? And to enable all the stuff you need for KVM, which is the kernel virtual machine, which can provide a series of optimizations that take advantage of the fact that if our host system is x86-64 and the system we're emulating is also x86-64, so it can allow the host, the guest system, to take advantage of our the full capabilities of our processor. So kvm guest.config. And that'll just modify our configuration file to enable those options as well. And then we can do make, do the same thing, and then just do no options will build it, but you probably want to provide attack J with nproc to allow it to use multiple cores. This takes a while though. On my I'm running on a computer that uses an Intel N100, so it's going to take around 10 minutes for me. So I have once again prepared the build itself. So if we go I can copy .prep, build Linux, copy everything in there. I'm going to need a attack R for recursive into our build Linux folder. Take a second, but then it's in there. And then we can see what would be produced by that build command. So the first thing you're going to look at here is this VM Linux. This is the uncompressed Linux kernel. It will have debug information enabled if you have that configuration, which I believe it is by default. So you can use this to debug the kernel if that's what you're interested in doing kernel development. But the zipped version of the kernel that we actually want to use is going to be in Arch x86 for us, boot, and then in here it's going to be this BZ image. Often that's renamed to VM Linux with a Z at the end when you put that in a boot directory, or if you look in your own boot directory on your Linux system. But BZ image is the compressed Linux image that we want. Okay, so we have a compiled Linux kernel. I'm going to take a second to draw the boot process just to understand what we're going for here. So in a standard computer, a modern computer, you're going to have some UEFI firmware. Oops. That's a horrible E. UEFI firmware. And that is going to look at the first EFI system partition. EFI system partition. And execute an EFI app. EFI app application, which will be either a stub or oftentimes it will be the bootloader itself. So this will get us to a bootloader. And then the bootloader is going to load into memory the Linux kernel, and the initial file system. And then the kernel is going to boot up and it's going to execute an initial, after it sets all its stuff up, it's going to execute an initial user space process. So the initial init process. So this is how you go from firmware to to running user space process for Linux in UEFI. Very, very brief overview. I'm not the most familiar with these early steps over here. I have played around with EFI apps a little bit, but I don't know everything. But over here, the init process, and the one we're going to look for is, I believe in the kernel configuration you can specify what init process to look for, but the general search path is going to be /init is the first process it's going to look for. So /init for us. And this is /init in the initial file system that it loads. Okay, and on on older systems, you would have a BIOS. I'll just write this out here for completion. BIOS firmware to boot sector. What's in the master boot record for a boot sector, 512 bytes that has a particular sequence in it, and then it'll load that into memory and execute that. And then that often you can't fit a bootloader in 512 bytes, so that'll load some other, set up some other stuff on the processor and load a bootloader from there. Okay, so for our use case, we're going to be running an emulator which is going to emulate a bootloader. So QEMU is going to emulate a bootloader. And so we just need to provide it with a Linux kernel, which we just built, and an initial file system. So the initial file system is the part we're going to be building next. So technically, we could set up a full virtual machine with like a full Linux distro on it and run our application on there just without an X server or Wayland server running. But it's going to be very learning a simple process like this is actually nice in my opinion, and also it's very easy to test, and it also ensures that our application will work with just a Linux kernel itself. And I'll show you we can actually even debug our process this way, and it's not too bad. Okay, so we have built a Linux kernel, we have to build an initial RAM file system. Okay, so our init process, if we think here, is actually just going to be our dump cycle executable. So currently, it just prints hello and exits. And so we're gonna dump that into an initial file system that can be loaded to the Linux kernel. So we're gonna make an initial RAM file system archive that the kernel can work with, and we're gonna do that with CPIO. So in dump cycle, we're going to make a directory. We'll call it FS. And in FS, we're going to copy dump cycle to fs/init. So in FS, this is going to be the root of our file system, our initial file system for Linux. And the way CPIO works is a slightly clunky old program. And what it does is it reads from standard in a list of files to put into the archive, and it writes them to standard out. So what we're going to use is we're going to use the find utility. So if we do find dot, it's just going to list all the files in the current directory. And we can pipe that to CPIO to provide it with the list of files to put in the initial file system, to put in the archive that we'll use as the initial file system. Okay, so we'll do find dot. We're going to pipe that to CPIO. The flag tac-o for CPIO says out, which means we're writing files out into the archive. Then we're going to do format equals new C. That's the format that the kernel expects. And then we're going to output this to .. I'll call it initramfs.cpio. 23 blocks. Now we can go to here, and to verify we did things correctly, we can do CPIO tac-I, which are reading files in from the archive, is what I believe the naming convention there is. And we can pipe in our initramfs CPIO, and it should have extracted the init file. And if we run that, it's exactly the binary passed in. So we can remove that, but we did correctly package our file system there. Okay, so now that we have an initial RAM file system and a kernel, we can boot it with QEMU. Okay, so we can do QEMU system x86-64. We're emulating a 64-bit system. We're going to pass kernel, and we're going to put a path to our kernel. That'll be in build Linux, arch, x86, boot, bz image, if you remember. And then we're going to do init-rd, initial RAM disk, which will be the initial RAM file system we just packaged, which will be dump cycle initramfs.cpio. And then I'm going to also enable KVM, because I'm on an x86-64 system and I built our kernel with KVM support enabled, just to make things run a lot faster. And then I'm also going to do display SDL, which is just something I need to have graphical support enabled by default on this funky chroot inside another system thing I'm working with right now. But you don't necessarily have to do display SDL. Maybe the default will work for you on your configuration. So if we run this, it's booting up, and we get a kernel panic. And the reason for that is kind of similar to when we first wrote our C runtime, if you remember. Before we did anything on the C side, the start C function, if we go back to here, before our start C function did anything and it just returned without calling exit, it was just jumping back into this code here. And if you remember, I put an undefined instruction here, but if I didn't put that, it would just execute the memory after and it would have crashed anyway. Yeah, so what's happened there was our start C function returned without calling exit and it just crashed. And similarly, our hello world program is printing hello world and then ending, and the kernel doesn't have anything else to do, so it's panicking. So all we need to do is modify our dump cycle executable to do something afterwards. For example, we can just put an infinite loop in here. Okay. So if we go back into dump cycle, I guess, dump cycle, we can make, and we can go through the process again. We can copy our dump cycle into fs/init. We can go into fs, and we can run that command again, find pipe to CPIO, output to initramfs.cpio. And now we have our initial RAM file system, right? And so we can run that QEMU command again with the same kernel and now our newly packaged initial RAM file system. And now it'll boot up, and now we get hello from init, and now it's just stuck in an infinite loop waiting. Perfect. So we have a method to build our executable and test it pretty immediately in a virtual machine that's running just the Linux kernel, and it's running our executable as an init process. And this is how we're going to be testing our game. The game we'll build will be one that you can run on any Linux system as long as it's able to take over an entire screen. It probably won't be able to run on a system that has a Wayland compositor or another display server running that's already managing the screens. But it won't have to run it as a init process, but we're going to test it as an init process just because it's a simple way to do it. There's lots of ways you could go about this, but this is the way I'm choosing to do it. And the last thing, a few more things. So the first thing we're going to do is we're going to add to our make file. We're going to add to our make file the ability to run and test this all from the make file. So let's add a rule to build initramfs.cpio. ramfs.cpio. So this is going to depend on dump cycle. It's going to depend on the dump cycle executable itself. And what it's going to do is that it's going to make a fs directory. We won't have the fs directory committed to our Git repo, so we're not going to assume it's there. Then it's going to copy dump cycle into fs/init, just like we did ourselves. Then it's going to change directory into fs, and the way to run multiple commands in sequence in a make file is you put a semicolon after the first one. Then it's going to run that command. I guess I'll just copy paste it. So if I find, let's copy paste that command. Okay. And that should work. Let's make it visible to the whole screen here. And perfect. So we can build initramfs.cpio, and let's add a rule to that. Let's make we'll just have initramfs.cpio built every time when we do all. And then we should add a clean rule for this too. So clean initramfs.cpio, and it's going to rmf initramfs.cpio and rmrf fs. It's going to remove that, and then we can just add this to our clean. So clean initramfs.cpio raff. Okay, so if we do make clean, oop. Probably have a dot phony. All clean. Ooh. Oh, I'm not in the dump cycle folder, of course. Sorry. Make clean. If we make, we should have our init.ramfs created correctly. Okay. So now our makefile will build us a RAM file system that we can test. And a useful addition to this would be maybe a makefile command that will run our virtual machine with the executable we tested. So let's grab our Linux kernel file and put it in this directory, and then we will target that with QEMU. So we're going to do init. We're going to do a rule test, which is going to depend on init ramfs.cpio. But otherwise, it's just going to do that QEMU command that we ran here. And just to make things a little cleaner, we can do a slash after each one of these. To make the lines relatively short. Okay, so now if we make test, it should build this. Now we just need to change this to be our init ramfs.cpio, and we're just gonna call this VM Linux. For right now, we're just gonna copy that into here. So cp // build Linux arch x86 boot bz image /VM Linux. Okay. So if we make test, it will run our executable in a virtual machine. Perfect. Last step, I'm going to show you how to debug code in our code in this virtual machine. So we are already building our code with debug symbols, right? With this tag over here. But to be able to debug, what we're going to have to do is we're going to have to stop the virtual machine before it runs our code, and then allow us to connect a debugger to it. And QEMU, thankfully, provides a built-in GDB server so we can use that. So let's run this QEMU command, and we're going to add the tag s symbol, which means run a GDB server on local address :1234. I believe it's shorthand for here. I believe I have in my yeah. So s flag. I could look this up elsewhere, but I knew I had already written this in an article I'd written. The s flag is short for GDB server at TCP :1234. :1234. Okay, so this will start run a GDB server, but it won't halt the kernel code. So we'd have to race to connect our kernel before our application actually ran. So we're going to add the tag S symbol, which means to halt before it runs anything. So if we run this, oops. Oh, you know, we're just let's do this in another. We're gonna make make test, and we're gonna have a make debug. And this is going to add tag s and tag s. We should probably add these to our phony lists here. Test and debug. Okay, so if we make debug, it's run the virtual machine, but it's halted. So now we can start GDB. So let's clear here. So in GDB, we're going to go to our dump cycle folder. We're going to run GDB dump cycle. So we're going to GDB and we're going to load the dump cycle binary into it. Now what we're going to do next is we are going to connect to the GDB server. So we're going to do target remote 1234. And it connected. And now what we're going to do is we're going to set a breakpoint. Main. I believe sometimes I have trouble with normal breakpoints. We'll try it here. Be main. And if we continue, yeah, see, it didn't work. I think you need to use a hardware breakpoint for this first breakpoint. So if we make debug, we target remote, and we do hbreak main, then this should work for this first initial breakpoint in our user space code. And we hit our breakpoint in main. So we are in the main. We are debugging the main function of our dump cycle executable inside the virtual machine, and we can see exactly what's going on. We can print, for example, argc. See that it's just 1. We can print arg v bracket 0. That's our /init. Cool. So we have a way of running our executable inside a virtual machine on a basic Linux kernel, and we can even debug it with GDB. I did not do this when I initially developed this game, so debugging was a lot harder. I actually copied a statically built GDB into the server, and I was running it in a little distribution I'd made. And I also used some simple printf debugging. But I think this way is going to make things a lot easier for us. If a problem goes wrong, we can just immediately switch to make debug, jump into the debugger, and see what's going on. Which is super useful for debugging low-level code like we're going to do here, where we need to really see what is the kernel giving us back, what are all our parameters set to. You'll see what's going on, what I mean when we get into making IOCTL system calls. Wonderful. So that's all I wanted to cover today. There's one last thing, which is to prove that this is not just a toy. You can actually make there's a bunch of different ways you can do this. I'm just going to continue out of here and then close. Okay. So there's a bunch of different ways, but I'm going to show you one way using GRUB that you can make a bootable USB drive or CD-ROM, whatever. That's technically the old technology we could have used, but and boot this same system we're running in a virtual machine on an actual computer. Now the main difference is the kernel, the default config kernel I built won't actually run on my Chromebook that I have here. So what I'm going to do is I'm going to copy in that article, the original article, compiled binaries. I provided a kernel that was configured to run on as many systems as I could figure out, and I'm not going to download that because it's a fairly big file as well. But I also have that in my prep folder. So if I cp.prep vm then we have this vm.tar.gz that you could download from my website. xf vm.tar.gz. So in this virtual machine is kind of the virtual machine I use to develop this game. But in particular, I'm interested in this VM Linux file here, which will run on this little Chromebook laptop that I have. And so let's build a GRUB ISO that will boot to my laptop. So how we're going to do that is we're going to make an ISO folder. ISO. So in ISO, we're going to make a boot folder. And in boot, we're going to copy vm/vm linux, and we're going to copy dump cycle /initramfs.cpio. Okay, so we have an initramfs and a kernel, and now we need to configure GRUB. So I'm going to make a GRUB folder, and I'm going to edit grub/grub.cfg. That's the configuration file name that you need. And then I have here the GRUB documentation open. And if I do menu entry, the commands for the menu are the first level of commands that we have available. So we only have menu entry and submenu entry here. And menu entry, you give it a title, there's a bunch of options, and then you put a list of commands in curly brackets. So what I'm going to do is I'm going to do menu entry dumb cycle. And then in curly brackets, we can specify a bunch of commands. And the first command I'm interested in is Linux, which is specifying a Linux kernel. And that's going to be in /boot/VM Linux, which is where we put it. And then I'm going to do initrd, kind of like our commands to the QEMU emulator. We're going to do /boot/init/ramfs.cpio. Okay, and you can specify kernel parameters to the Linux kernel if you want here. We're not going to do that. Actually, you could specify kernel parameters to Linux kernel, and if they're not parameters that the Linux kernel recognizes, they'll pass those on to our init process. So we can actually specify arguments that get passed to our init process, like our dumb cycle application, which we might play around with later. But for now, we'll just do this. Okay, the final step is to use GRUB to actually build an ISO file. Okay, so we're going to cd dot. So if you remember, if you do find ISO / you can see that our ISO folder, remember, it's a boot folder. Inside the boot folder is VM Linux and initramfs, and then a GRUB folder containing our GRUB config. That's all we have. So this ISO is kind of serving similar purpose to our FS directory in our when we built our initial RAM file system, whereas it's going to be the root of the file system is going to be written to the ISO boot drive. So the tool we're going to use is GRUB make rescue, and we're going to output into I'll call it dumb cycle.iso, and we're going to pass it that ISO folder, and it worked. And now we just need to test. Does this work as expected? So one way we can test it is if we look at our QEMU command. Instead of passing an initial RAM disk and a kernel, we can tell it to boot from this ISO file. And the way you do that is you do boot D. This is saying boot from the CD-ROM drive, and we're going to do CD-ROM dumb cycle.iso. And I'm not going to stop for debugging this time. And hopefully we configure things correctly. So we get a GRUB boot menu, as you may have seen many times if you've ever run a Linux system that runs GRUB. And then we hit enter on our dumb cycle, and hopefully this will boot from our kernel and run our hello from init, and it did. Look at that, hello from init right down there. Okay, one final step. I have a USB drive plugged in, and it's in /dev/stc, and I'm going to, just to make sure else be okay. As you can see, it's still kind of partitioned. I've already tested this part out, so technically it already has the boot drive installed on it, but we're going to do it the same anyway. So we're going to sudo dd. All we have to do, this ISO file already has the partition table and the partitions and everything written to it, so we just need to copy the raw bytes to the drive. So we're going to do if is dumb cycle.iso. OF is going to be dev/stc, and then block size I'm just going to do 1 megabyte for okay. And it wrote. So let me grab my laptop here and grab my drive. We're going to have to enter the boot menu here because I believe this laptop, I do use it. So it's not set up to enter the boot menu. Let's go here. We're going to go down to boot menu. We're going to select my Kensington Data Traveler 3.0 here, which is my USB drive. And then we're going to hit enter. Got a GRUB menu. And here, you see up there, hello from /init. So we're able to boot from a real system with the same process we did for our virtual machine testing. See you in the next one. It won't be as long of a wait. I figured out how to make videos now, so